Now that I've outlined the structure and functionality of the LockManager server-side components, let's take a look at their implementation. We'll focus on the LockManagerController and the LockManagerService classes that are part of the LockManagerApplication microservice, which you can get at this link below. This is the particular part we're going to focus on, which is the implementation in the server folder in this particular project. So we're now in the server folder in the EX5 project, and let's take a look at the various implementation artifacts, starting with the LockManagerApplication, which is really no surprise here. This is just your typical entry point into the distributed lock manager. Doesn't look any different from all the other microservices we've looked at over time. Likewise, the controller is pretty straightforward. This is what we also looked at in the previous part of the lesson. This controller is auto-wired to the LockManager service, and it's got a bunch of methods that just simply forward to the LockManager service to do their thing. No real surprise here. Again, we've got the get mapping, we've got the post mapping, and so on, with all the other things you've come to expect from implementing controllers. The interesting part of this implementation, however, lurks in the LockManager service class. And as you can see here, it's got a field that's the executor service implementation that is going to be implemented with a new virtual thread per task executor that's used to run incoming requests off of the servlet thread from the servlet thread pool. We also have the array blocking queue, which we use to implement our semaphore semantics without requiring detailed knowledge of synchronizers. And we do that to limit concurrent access to a fixed number of available locks. And we'll see how that fixed number is set here in just a moment. Speaking of the fixed number setting, here's the create method, which is essentially a virtual constructor that's used to initialize the lock manager. And it's got takes a permit count, which is the number of lock objects that we're going to be managing. As you can see, we check first to see if we've initialized ourselves at all before. If we have not, available locks will be null. If we have, but the size of the available locks differs from what we're requesting here, either bigger or smaller, we're then going to go ahead and go into this block of code. Now, if this is not the first time in, if we've already initialized available locks and it's not the right size, then we go ahead and clear it so we can start with the right number. And in either case, whether it's the first time in or it's a subsequent time with a different permit count, we make ourselves an array blocking queue that contains this many permits, and it has its fair flag set to true, which means that threads that wait on this array blocking queue will wait in, first out, or FIFO order. Once we've got the available locks queue initialized properly, then we go ahead and we add the lock objects to the available locks queue. And we do that by calling the make locks factory method, which takes the permit count, makes a stream that goes from 0 to 1 less than the permit count. We convert each of those numbers into strings, and then we pass those strings into the constructor of the lock class. The lock is what's actually sent back and forth between the client and the server. And so you can see here what we have is we have an ID, which is the ID of the lock, and we've also got constructors which set the ID, and we have a toString method that takes the ID and indicates it's that particular lock number. Now, if this was a production system, we would spend more time doing fancy schmancy things to make this opaque so that clients couldn't really see what was inside of it. We would also spend more time making it so that clients couldn't fabricate or falsify or masquerade the lock results in some strange way, but we're just doing a simple example, so we're not going to focus on that right now. The result that comes back from this map call will be a lock initialized with the string ID. We convert that into a list and return that here and assign that to the available locks field. Now, in this case, in this arm, we see that something changed as a result of the call, namely available locks. So we return true, Boolean true. Otherwise, nothing changed, so we returned Boolean false. And that's just a way for the caller to know whether anything changed. By the way, I had some fun using ChatGPT to simplify this code and make it so it was very clean and non-redundant. So I used it for refactoring, which is a nice use of ChatGPT. Let's now come and take a look at the acquire method that returns a single lock. And you can see it returns it as a deferred result. Remember, deferred result is this clever mechanism that Spring supports that allows you to do computations off of the servlet thread, but while still deferring the result until the processing is done in that background thread. So let's go ahead and see how this works. The first thing we do is we make ourselves a new deferred result object. Then we're going to go ahead and submit a task to run in a virtual thread. But notice how that this deferred result object is actually passed back right away from the caller. So it looks at first glance like it's returning something back to the client. That's not in fact what's happening. What's happening is that it's returning back to the controller implementation mechanisms that Spring provides. And that is then going to wait for the result to be set on this deferred result. And that's going to be done in a background thread. In particular, it's going to be done in a virtual thread submitted to this new virtual thread per task executor. So all this code runs in this virtual thread. The first thing we do is we check to see if there's a lock ready and waiting for us by using poll, which is a non-blocking call. And if we get lucky and it returns non-null, that means we got the lock. And so we log that, and we'll do some other stuff below. If we didn't get lucky, then we have to go ahead and block using the take method. So unlike poll, which returns right away with either a null or a lock, take is going to block until a lock is available. So that may block this thread, but that's okay because it's running in a virtual thread in the background. In any event, either through non-blocking or blocking, we got ourselves a lock. We then go ahead and set that lock as the result of the deferred result, and that will cause the controller implementation mechanism on the server side that Spring manages to return this lock back to the client. So that's acquiring one lock. Let's go and see how we acquire multiple locks. So this version of acquire takes a permits parameter, and what it's trying to do is it's trying to return a list of locks. So it has to acquire that many locks in order to return. Once again, we use deferred result. As you can see, we make that here to hold a list of locks, and we return the deferred result right away. And then we have a background thread that we submit to the executor, which is going to do the magic algorithm to acquire the number of locks we requested. And this is a very clever strategy that uses non-blocking acquisition and essentially a kind of a transactional approach of being able to give back locks if we're not able to make forward progress. So let's take a look and see how this works. First thing we do is we make ourselves a local array list of locks, and then we're going to call a helper method called tryAcquireLock repeatedly until we're able to acquire as many locks as the permits parameter requested. Now, what makes this interesting is we might actually have multiple threads that are calling this acquire method simultaneously, and they need to work correctly even if they can't get all the locks they want in one fell swoop. And we need to do it in a collaborative way so that we don't end up with deadlock, where one thread's holding a lock and trying to acquire another lock holds a lock and is trying to acquire another lock, and neither one could make progress because each of the threads has the lock the other one wants. For example, if you had two threads, each of which were trying to acquire two locks, and you only had 3 locks, then the first thread could acquire 2, the second thread could acquire 1, and then neither one could make any progress unless they do some kind of cooperative behavior, which is what the tryAcquireLock method does. So you can see tryAcquireLock is passed in the list of locks we've acquired thus far, and then what it does is it tries to get a lock in a non-blocking way using poll. If it succeeds, if it got a lock, it adds that to the list of acquired locks and returns the size of the list. However, if it was not able to acquire the lock because there wasn't one available, what it does to be cooperative is it goes ahead and it frees up all the locks it currently owns, clears out the acquired locks list, and then returns 0. And what that does is that indicates to the caller that we haven't acquired the locks and we have enough locks and we have to keep spinning here and continue trying to acquire. So this approach is very clever at avoiding deadlock. However, you can actually do some extra busy waiting. So it's kind of a compromise. As I mentioned in an earlier part of this lesson, not the only way, not the best way to implement a semaphore with multiple counts, but it was sufficient here because we're trying to do this without requiring detailed knowledge of Java synchronizers. The end result, when we get the locks we want, is to call setResult on deferred result, passing in that list of locks, and then that will then be an indication to the controller implementation that it should take that result and send it back to the client at that point. There's a couple other methods to look at real quick both of them release one or more locks. So here's the version of release that releases a lock. And what it does is it calls the offer method, passing in the lock. And offer is a method that does not block, and it returns true if it was able to put the lock back into the array blocking queue, and it returns false if that queue was full for some reason. Now, the queue should not be full if the client follows the protocol correctly of acquiring and releasing the locks. But if they don't, then this is a way to make sure that we know that that happened, that there was a problem. So that's releasing one lock. Here's how we release multiple locks. We take the locks list, turn it into a stream, and then for each of the locks in the stream, we go ahead and call mAvailableLocks offer, which is going to try to put the lock back into the array blocking queue in a non-blocking way. And remember, that returns true if it's able to do that successfully. So if all these calls return true, then all matches true. So we return a Boolean of true. Otherwise, if there was some problem in putting one of the locks back, then it'll return false. The only other last thing here is just to look at the constants class. You can see it just defines the endpoints for the various endpoint handler methods like create, acquire, release lock, acquire locks, release locks. And it also defines the base URL for the LockManager server itself. So that's a walkthrough of the server side. Shows off a couple of very interesting things. In particular, shows off how to use the mechanisms here that do deferred results. It shows how to run things in the background using the new virtual thread per task executor. And then we also saw this clever algorithm down here to acquire the locks in a non-blocking way to avoid deadlock. And once again, I should point out that ChatGPT and I had some good fun working together, coming up with this implementation you see here. And it didn't get it right at first because it kept generating code that would deadlock. But when I reminded it that that was a problem, it came up with a better solution, and I massaged that into what you see here.